All right, in this one, I'm going to go through the stable vector or vector of stable probabilities with Markov chains. This is part 3, so make sure you know how to do transition matrices and state vectors. I'm also going to go pretty fast, so if you've not seen the stable vector stuff before, you are going to get lost. And if you don't do more problems after this, you will not do well on any problems on the test that ask you to do anything with stable vectors. So make sure you do your work for class, do your homework, and study, but this is a good review. All right, so here we go. Sometimes the Markov chains have stable vectors. And the idea here is that if you're going to try and predict the probabilities of being in a certain state or really far time away, eventually the farther and farther you go out, those probabilities are going to start to level out and start being stable. So one way they'll visualize it is if we're over here and we have different observations each time we do a transition, eventually those observations and the probabilities of being in each stage is going to level out into the same number over time. So it's sort of a long-term state vector, but it's different problems than state vectors, so don't get them confused. The stable vector is represented by the letter W, and the equation we're going to use is W times P, the transition matrix, is equal to W. So this is saying this is your probability of being in each stage. No matter how you transition, you're going to end up probably in the same stage. So if you don't understand all the theory behind it, that's fine. It's called upper level math, but make sure you know how to use the equation. So we'll go through an example. They're usually going to give you a transition matrix like this one right here and ask you to find the stable matrix. So I just plugged this into our equation. W is X and Y because those are our variables. They're on both sides, as is W, multiplied by P in the middle here. All right, so the first thing we're going to do is convert this into equations that we can use to use it on systems of equations. So the equations we're going to use are the ones you would use in matrix multiplication. So if you wanted to, for instance, get this value by doing the multiplication here, you'll take this row, multiply by this column to get this value. So that would give you the equation 1/3 x plus 4/5 y equals x. The other equation will be if you were to find this value, you would take that row times this column, and it would be this equation. So I wrote here that you only need to keep one of these. If you were to try to use these two as your system of equation, they're going to cancel each other out and you won't be able to solve for any variable at all. You can try it if you'd like. But what I'm going to do is just throw one of them out and only use one of these equations. I'm going to use the one on the left here. And I'm also going to take this time to make this look a bit nicer by subtracting an x off of both sides. So that leaves me with 2/3 x plus 4/5 y equals 0. So I converted this into this, and we're going to throw this guy out because we don't need it. We do need a second equation though, and we can use x plus y equals 1 because a stable vector is a probability vector. So when you add these two values together, they're going to equal 1, just like a state vector. So this is our second equation for our systems of equations, which I then wrote down here. Here are our two equations. And then I did a systems of equations to solve for y. And if you need help with that, those are in previous sections of finite. So now we have what y is down here. And from there we can figure out x by plugging it into one of our equations. I plugged it into x plus y equals 1, so x plus the 5/11 equals 1, leaving x to be 6/11. And now I can finally plug it back into our stable vector. So w is going to be equal to 6/11, the x, and 5/11, the y. So this is our stable vector for that transition matrix that we gave us in the very beginning. Here would be the answer. In some problems, they'll ask you to find the stable probability of being in state 2. So state 2, stable probability is there. Or they could ask you for the entire thing. In order to check this, as there are often ways to check things in finite, you can plug it back into the formula WP equals W. So here I just plugged in our W, I put in our P, and if you were to do the matrix multiplication, so this row times this column for this value, this row times this column for this value, you would once again get this over here to equal 6 over 11 and 5 over 11. So since our W's are the same here and here, that means yes, we did the right work, this is a good job, and we have the correct stable matrix. Okay, a couple different caveats on these problems. First, we're going to look at this one. If you were to do the transition matrix for the 1,000 steps, so p raised to the 1,000th power, or any huge number, so you just did p raised to infinity to represent a big number, it would be approximately equal to your stable matrix over itself. This is saying that if you were to try and step forward 1,000 times and guess which state you're going to be at, it doesn't matter where you started. It doesn't matter if you started in row 1 or row 2. You're going to end up with the same probabilities of being in each state. Next, we'll look at this one. I wrote that if you were to multiply p raised to a huge number by any starting state vector, it would look like this. So what I did was I took this guy, we already proved or talked about how that would be p raised to a big number, and multiplied it by some random starting state vector I made up. And it gave me my stable vector. So this can prove that no matter where you start, if you tried to predict way out into the future, so p stepping 1,000, a million, 100 forward, the probabilities of being in state 1 or state 2 are going to be the same every single time, no matter where you started. So you can change this however you want. Multiplied by this, it's going to be 611 over 511. Okay, so those won't come up too much, but they are interesting facts that could get woven into some hard problems. You'll also see this with Markov chains with 3 states. So you would do the same exact process. You would convert your W times P into 3 equations and throw out the worst one as we did here. So we only had 2 equations to worry about here. We had this equation and this equation, we threw out 1. If you had 3 variables, you would have 3 equations and you would still throw out 1 and then use x plus y plus z equals 1 as your 3rd equation. All right. Here is the next really important part. Not all Markov chains have a stable vector. They have to be special in order to have a stable vector, and those are called regular Markov chains. A regular Markov chain must satisfy this condition, that at some point, a power of the transition matrix must have all positive values in it. So that means at some point, we have to have, if this is our transition matrix, all of these numbers have to have a positive non-zero number. And it can be any power. So how do we figure out if a given matrix is regular? We're going to check powers of P until all the zeros go away, up to the power of n minus 1 squared plus 1. So this just helps you find a stopping place so you're not checking forever. So for example, if you have a 2 state, you'll go up to P at 2. For a 3 state, you'll go up to P5, and for 4 states, up to P10, etc. Here in this example, we have a 3-state Markov chain. So if we have 3 states, it was 1 minus n squared. So 1 minus 3 is 2, squared is 4, plus 1 is 5. So we have to work up to the power of 5 for our transition matrix here. In order to figure out if any power is going to have all positives, you just got to keep multiplying. Given this as our transition matrix, we're going to start by finding p squared, which is the same thing as doing p times p. And a trick here is because we don't really care what the numbers are actually going to be. We only care if they're going to be positives or not. So all I'm going to mark is a plus sign for positives and a 0 for zeros. You'll never have a negative value because these are probabilities and you can't have a negative probability. So I just copied the pattern of p twice. So you'll see for all of the positive numbers, I have positive signs and multiplied that by itself. So now we're going to go through and look at what we would get if we were to multiply this. And it's hard to do on Zoom, but try to follow along. So for this value, we're going to have positive times a positive plus positive times 0 plus 0 times a positive. These two are going to cancel out and be zeros, but this first positive times positive is going to give us a positive value. So I'm going to write a positive here. I'm going to move 1 over. This is going to be this row and this column. It's going to be a positive times a positive. That means we have a positive number already, and even if we add zeros to it, it's going to stay positive. Next, we're going to look at this number on the right. Positive times 0 is 0. Positive times a positive is a positive. So that means we have something in here, and we're good. Moving to the middle row. This value here is going to come from this row. So 0 times this column, a positive is 0. 0 times 0 is 0. Positive times positive is positive. Add them all together and you'll end up with a positive. Middle, taking 0 times a positive is 0. 0 times 0 is 0. And positive times 0 is 0. So we're going to be stuck with a 0 here, since we got all zeros for all 3 of those multiplications. For this spot, we're going to have a 0 times a 0 plus a 0 times a positive plus a positive times a 0. So all 3 of those got canceled out to be zeros and will add up to be a 0 as well. Last row, this one's going to be positive times a positive, which is going to end up being positive. This one's going to be positive times a positive. So even though these are zeros, we already have a positive in here. And the last one is positive times a 0, which is 0. 0 times a positive is 0, and 0 times 0 is 0. So all of those were zeros, leaving us with a 0. Okay, so that's one iteration of multiplying the p's together. And what we ended up with was more positives. We did better, but we still have some zeros. So we have to keep checking. We're only at p squared. We got to get up to p to the 5th power. So what I'm going to do here is just get up to p squared times p squared, because that's going to equal p to the 4th. And it's the same exact process, taking 2 of these and multiplying them by each other, and then going through what we just did. To save some time, I already worked that one out. So what you can see here is that I copied this guy twice here. I went through and did all the multiplication, and what happens is those zeros all get turned into positive numbers. So we can see that p to the 4th has all positive entries, which satisfies our condition of some power of p having all positive entries. So yes, this matrix is, this Markov chain is a regular Markov chain, and it will have a stable state vector. So that is all of chapter 3 we're going to be covering. And from here on out, we're studying for the final. So I hope this is helpful. Keep coming to PASS for practice problems and final review sessions, and good luck with everything. Thanks for watching.